Good morning, everybody. It's time to start. Welcome to the last colloquium of this academic year. And we finish with a big splash, talk about accelerating global warming. The speaker today is Professor Szymon Malinowski, who is an expert on climate change. He's been a member of various advisory boards, and he co-authored a book on climate change, Nauka o klimacie, and a portal under the same name, which is the biggest and best source of scientific information on climate change in Polish internet. He's also an expert on dynamics of clouds, and today he will speak about why is it warmer than we expect it to be. Please.
Thank you very much. Can you hear me? Okay. Thank you for the invitation. I'm just popularizing the climate science. I'm a specialist on atmospheric turbulence and cloud physics. So if you want to look into my papers, the papers are about this, but it's closely related to climate. And since in Poland, there is not a single institution on a governmental level, or there is no real physical climatology course or physical meteorology course in any university. So we are doing with some colleagues actions trying to provide better physical ground information on what's going on around us. And I will start with the climate system. Oops, there are some students coming, so I will wait a moment. Oh, it's in English and will be more complicated than typical talk to the secondary school students, but I hope you can ask questions. And thank you for coming here.
Lots of space here. Please go down.
Okay, so I will continue, and I will go. I will go with a slide I have shown many times at different occasions. And this is just a demonstration of the climate system from a special perspective, from the special perspective of the sun. So this is not a Photoshop, this is a real image taken from the spacecraft, which is called Deep Space Climate Observatory. And this spacecraft is positioned in the Lagrangian point 1 between Sun and the Earth. So this is the place when the gravity acceleration towards the Sun and Earth balances. And it always looks at our planet from the perspective of the Sun. And this particular photo has been taken in a moment when between the spacecraft and our planet, the Moon passes through. So it shows a kind of striking features of climate systems on these two celestial bodies, which receive the same amount of solar radiation per square meter area. And at the first glance, you can see something which is not very obvious to the majority of us. The Moon is dark. It's the brightest after the Sun object on the sky, and it seems very, very bright. Nevertheless, it's much darker than our planet. Generally, the albedo of the Moon is about 15%. So it means that about 15% of the solar radiation reaching the surface of the Moon is reflected back to space. In case of the Earth, it's much more. It's about 30%. But if you look carefully at this image, you can see that it is not the properties of the surface of our planet, but the property of some things present on the surface or in the atmosphere. It means small crystals of ice or droplets of water which either hover in the atmosphere or are deposited on the surface. So, big part of Earth's albedo is related to presence of clouds and ice. What can you see more? You can see blue, and blue is not the ocean. It is the sky above the ocean. It is the atmosphere in which blue part of the visible spectrum is being reflected or scattered back to space. And it's also scattered in all directions, so we see blue sky on our planet. I will not speak about green, which is very unique in the universe. Clouds are also pretty unique, I must say, this kind of clouds. If you know some exoplanets, we don't know many planets with such features. So there are, there is the Earth's surface, which is bit corresponding to the surface of the moon. There is water, and there is a layer of the atmosphere. Water means oceans, and the atmosphere are fluids. And fluids are not present in the moon. And fluids are very specific since they can carry different properties with the flow and redistribute them on the globe. So this is another very, very specific thing of the planet. So how much of the fluids do we have? We have, the atmosphere seems very, very thick from the bottom, but on this image you can see that it is not very thick. It's hard to see the edge of the planet, of the atmosphere. But if we compress the atmosphere to the density of the water, it would be 10 meters. On the other hand, the oceans cover 3/4 of a globe, are in the average 4 kilometers deep, so there is 3 kilometers in the average of water on our planet and 10 meters of the atmosphere in corresponding mass units. So we have to know all these details before we will go how the climate system works. And what is the climate system? The climate system is everything which is on the planet's surface, means atmosphere, oceans, whatever covers the surface, and not much deeper. And as you know, any body which temperature is greater than absolute zero emits radiation. What we can see here is radiation emitted from the sun and reflected or scattered by the Earth. But of course the Earth emits also its radiation because of different temperature. This is infrared emission to space, and it's a kind of information about in units watts per square meter of the numbers which are present in which we could observe our Earth from the sky. So how does the planetary system work in principle? Basic thermodynamical principles. It works like this. It receives the low entropy, high quality energy from the sun. It reflects part of the energy back. So it does not come into the climate system, and it does not participate in different reactions in the atmosphere, in ocean flows, and so on. And some part comes to the space, and then it hits the surface, and it increases the temperature of the surface and the climate system. And since this temperature is above zero, it starts to radiate to space. But we have the atmosphere, which have very specific properties, which absorbs some of this energy. This energy is high entropy energy of worse quality. Nevertheless, it warms the atmosphere and emits radiation back to the ground. This is called greenhouse effect, and back to space. If you look for the energy balance, like in any balance of the thermodynamical system, closed thermodynamical system, increase of the internal energy due to positive or negative balance of incoming and outgoing energy is being reflected by the temperature, since the temperature is the intensive measure of the internal energy of the system. So, of course, if you think about transmission through the atmosphere, this is the idealized emission from the sun, and what is transmitted through the atmosphere part is being reflected and absorbed in the atmosphere, and this is light which gets to space. It warms the surface, and it's being emitted from the surface, and due to presence of the in the atmosphere, water vapor, carbon dioxide, ozone in some part, methane, nitrous oxides, and other gases, there is a lot of absorption of the atmosphere. Atmosphere absorbs a lot of solar radiation and transfers the energy back to the surface. So this is a kind of simplified picture of different planetary. It was working. Maybe I should disconnect this mouse.
Nie, dlatego, że ma pan tryb ekranu, rozszerzenie, a nie dublowanie.
Okay.
I to widać tu, a nie tam.
Okay, so
Mogę przynieść las akrecyjny.
to proszę. So generally we are talking, depending on the atmosphere, we are talking about these red arrows coming to the surface, which give additional energy to the surface. But as you can see here, in this example of multi-layer atmosphere, which absorbs a lot of thermal energy, so it's so-called multi-layer, simplified multi-layer model, you can see that first. If you go from the outside, what is being emitted to space depends on the temperature which is in the upper part of the atmosphere. And what goes to the surface depends on the temperature of the lowest layers in the atmosphere. And the distribution of absorbing gases along height shape the energy balance on the different layers in the atmosphere. And what is pretty interesting, a Nobel Prize from 2021 to Syukuro Manabe was about the distribution of the energy in the atmosphere, especially in the lower layers, because of radiative transfer and other mechanisms transporting heat in height. So generally, these valves or knobs we have on the input, on the output, are pretty complicated by themselves. So you see here a kind of behavior of the knob on the input in vertical, depending on, Syukuro Manabe has shown that if the Earth's surface temperature would grow due to increased solar radiation, the profiles would be different, and we observe changes in the profiles of temperature in the atmosphere according to his calculations. And the second thing, which is very important about the valves and about the processes on the Earth, is the redistribution of energy. The redistribution of energy, since what we see here, it's a kind of single column approach. So we try to look through the atmosphere, what is the energy balance profiles of temperature and transfer in vertical. But we have distributions in the atmosphere and in the ocean. And of course, we know that they are important for the climate. But there are some misunderstandings about the level of importance of those. Despite the fact that the ocean has there is, in terms of mass, is 3,000 more of water than the air on the planet, and the specific heat of water is 4 times bigger than the specific heat of the Earth. So the heat capacity of the ocean is 1,200 bigger than heat capacity of the atmosphere. Atmospheric transport from the regions when we have surplus of incoming energy close to the equator to the poles, when generally we have very weak energy supply from the sun, and the energy, radiative energy supply is from the atmosphere, is in the atmosphere, dominating in the atmosphere, not by the ocean. And this is because the fact that we have just one ocean which can mostly openly redistribute energy between the hemispheres and between these regions. This is very, very specific. We will come back to this in a certain moment. Marek Trippenbach was asking me to give information about this, so he's not here. I will not elaborate about it. So generally, if we go to the energy balance in the single column, average for the Earth, average square meter of the Earth, this is incoming solar radiation. This is what is being absorbed in the atmosphere, partially in far ultraviolet or close ultraviolet by oxygen and ozone, and partially by absorbing aerosols. This is what is being reflected. As you can see, reflection from aerosols and clouds is much larger than the reflection of from the ground. This is what reaches the ground in the average. This is what enters the ground. This is heating of the climate system. This is the radiation emitted to space, which is almost all absorbed in the atmosphere. Atmosphere is non-symmetric, so it emits much more to space than to the surface, but there are two more energy transfer processes which are important, at which interplay with the atmospheric and oceanic circulations, which are related to evaporation and latent heat release in the atmosphere. So the amount of energy which has been delivered to the atmosphere in this way is just proportional to amount of precipitation. And sensible heat means whatever we know, convection. So, and what we observe, or at least observed in years 2005-2015, was an average imbalance of our planet. Energy balance of the planet means it absorbs 0.7 watts per square meter, then emits back to space. So the temperature should increase, especially temperature close to the surface, which we measure very often, and we use it as a signature of climate changes, and it is justified from the perspective that we live in this layer close to the surface, so this is what affects us. But from the terms of the energy balance is what gets stored into the whole system. And this is a kind of simplified energy balance, which of course you cannot do accurately, since clouds depend on evaporation and on sensible heat. How the energy balance would look like without clouds and aerosols present in the atmosphere. So if you compare these numbers, you could see that the albedo of our planet would be much smaller. So it means that clouds play a very important role in the energy balance of the system. It's not only the greenhouse gases, which are on the output knob of the system, but also input knob of the system is very, very important for any kind of climate changes. Just you can see the numbers here, amount of energy in the average. This is the average for the whole planet, reaching the ground and reaching the ground from the greenhouse effects. And these are some examples of the measurements on the roof here. We continuously monitor, radiative fluxes in different wavelengths on the rooftop. And you can see two examples, one from June previous year, when we had such a situation that we had cloud cover in the morning. You can see the scale watts per square meter. This is incoming solar radiation. And to the surface, this is a model what should be on the top of the atmosphere. This is what reaches the ground. The green means it's mostly scattered radiation. You can see such a plots every day online, yes, on our site. So we provide them on a constant basis. So then you can see that clouds are broken. You have huge fluxes of solar energy and some clouds, which are pretty thick and big variability. Then you have very long day. And you can even see that during the day, you might have more radiation than comes directly from the sun, since you have some scattering from sides of the clouds, of course, reaching the ground. And then you can see the measurements of the incoming infrared radiation in watts per square meter. So this is direct measurement of the greenhouse effect reaching the surface. And this is a kind of the day in December. Look for the change of the scales and look for the amount of the solar energy reaching the ground. Nevertheless, still there is huge amount of energy coming from the infrared. So you can see that even in a small scale, you have huge variability on the surface related to clouds and aerosols. So generally, this kind of observations are being made all over the world, and this is a big network of these observations. We are not unique. There are many places which provide such an information. We have satellite informations and so on. And then you can see a kind of measurements or averages. This is from NASA side, long-term average of the total net flux of the surface. You can see that in the majority of the places, this is above zero. So the total flux, radiative flux, both from solar and from infrared. But you remember that we have this evaporation, latent heat, and convection, which takes the energy from the surface. So it's not surprising that this is not symmetrical. This is not shortwave flux, means from the sun. And of course, the minimum in many year cycles is close to the poles. The maximum should be close to the equator, but it is not due to the presence of clouds there. And these are some specific regions I will focus more, which are kind of coolers of our planet, which are very important for the understanding of climate change and other processes. And this is, you know, in the region when there is small amount of water vapor in the atmosphere, water vapor is most potent greenhouse gas. You see huge emission to space and the greenhouse effects weaker there. So these are more or less the energy fluxes. But from the perspective of how it works, what is important are forcings and feedbacks in the climate system. So what governs the climate is the distribution of the energy, incoming, outgoing energy on a global scale, says about global warming and so on. On local scale, it says about transmission through the atmosphere and greenhouse effects, and also horizontal transport of heat by atmospheric and oceanic circulations. But oceanics and atmospheric circulations are mechanisms which are driven by this temperature difference or energy inflow difference to the system. And these are some feedbacks in the climate system. But what may change the energy balance as a forcing? So forcing is something from outside the climate system, which may produce changes in the energy balance. So for instance, there are Milankovitch forcings. There are forcings due to changing solar activity. There are volcanic forcings, which are pretty strong, can be pretty strong on short-term scales and on the input basis after bigger volcanic eruptions, and which have been important for a very long time scales in geological history of the planet. And there is one more forcings which changes the properties of the atmosphere in both ways, in reflecting and absorbing part, and this is anthropogenic forcing. And this is a very specific forcing which has never existed by the planetary history to the moment in which we learned how to burn carbon, present both in life systems and in sedimentary rocks coming from the earliest life systems, and change the properties of the atmosphere, adding to the atmosphere the gas, which is also very potent greenhouse gas, but very hard to remove. And there are feedbacks. For instance, all things related to water are feedbacks. Since you see that water, there's much more water than the air in the atmosphere, and amount of water in terms of small particles which reflect in terms of water vapor, which is potent greenhouse gas, and small particles which reflect the solar radiation, which influence the input, well, this is governed by Clausius-Clapeyron relation. So whatever changes the temperature of the ocean, more water vapor will be in the atmosphere, but not more than Clausius-Clapeyron relation allows. So it's very strong and very strong feedback. And it's also really fast feedback. And slower feedback, but also fast and important, is related to the water which reflects solar radiation, either floating on the sea surface or being deposited in landslides. If you would like to see generally feedbacks, forcing feedbacks in the climate system, so we force the climate system, and they are feedbacks in the climate system, estimated on the base of many physical modelings. You can see these feedbacks generally on the top of negative feedback is Planck feedback or Stefan Boltzmann feedback, since amount of energy being emitted to space is proportional to the force power of the temperature. But all other critical feedbacks are positive. So whatever forcing is, these feedbacks may influence the, may multiply, positively multiply the effects of these forcings. Unless we will go to the feedback, the net feedback is slightly negative, but these feedbacks are very important. And you can see that for the clouds, the uncertainty range is much larger than due to the other feedbacks. Why? Because clouds consist of tiny droplets forming on aerosols. I will say about it more. So how do we understand forcings and feedbacks in a climate system? This will be an example from 800,000 years back. And this is a global temperature anomaly estimated from proxies, means some footprints which have been left by past climates of the planet, and reconstructed calculating forcings and feedbacks in the climate model system. And this was the assumption that the forcings were due to Milankovitch cycles. This is more or less the first humans appeared here, and these are consecutive glacials, and this is radiative forcing anomaly. Radiative forcing means the changes in the radiative transfer in the atmosphere to the globe from certain chosen moment, which is here the pre-industrial era, more or less stable. So you can see feedbacks due to albedo of ice, means ice sheets, of change of the sea level, so it also changes the albedo. From the presence of the aerosols in the atmosphere, we can reconstruct from the information in ice cores, and changes in the most potent stable carbon dioxide in the atmosphere, which dissolves according to Henry's law much better in colder waters than in warmer waters. If you add all these feedbacks related to these forcings, you end with the radiative fluxes like this. This is output valve. These are input valves. Total effect is like this. And if you translate it to the temperature changes, you get the effect like this. There are many works like this. I just have chosen this because the picture here is very nice to illustrate how does it work. So we know more or less basic forcings and feedbacks. And look at the feedback from the carbon dioxide here. And you can now look this feedback as in terms of concentration of carbon dioxide in the atmosphere during these ice ages, and then compare it, since now the carbon dioxide concentration in the atmosphere changes due to different processes on the surface, due to this anthropogenic forcing. So you can see the magnitude and speed of increase this anthropogenic forcing. So if you look for the history of the civilization till 2019, you have more or less what you see here. This is the best reconstruction of the temperature surface planet with the uncertainty from many reconstructions from pages 2K is very big international collaboration on the reconstruction of the temperature changes of the planet and temperature growth. And this is the corresponding time period of the carbon dioxide concentration. If you will focus on this period from here, then you can see a kind of a history in radiative forcings of the planet, positive and radiative forcings of the planet. The forcings for the sun was in this scale negligible, on the order of 0.1 watt per square meter. So the biggest forcings were from the aerosols, especially major volcanic eruptions, and they were on the input. They are from the increasing energy of greenhouse gases, mostly anthropogenic, rapidly increasing here. And also, what we can see, you have negative feedback with how big uncertainty range from the presence of aerosols and clouds in the atmosphere. So this is the effect on the input valve. And of course, we can make a kind of numerical simulation. This is a kind of way proposed another Nobel Prize in physics from 2021, Klaus Hasselmann and the others, how to distinguish, and this is how would the temperature change would like due to natural forcings, and how does it look on it's the average from about 70 different Earth climate models in these models, which account for these forcings and feedbacks I have shown you. And this is one of the temperature series I'm going to say. So generally, what we had till 2019, we observed 1.1 degree from the pre-industrial, and we can model it exactly the same with bigger uncertainty range. We have positive increase due to greenhouse gases and decrease due to aerosols and changes in cloud properties, and variability due to internal variability, El Niño, La Niña mostly, and other variabilities. So you can transfer it into energy forcing. I will not speak about it, but the problem which we observe now, since we observed energy imbalance from space, is that the energy imbalance we are talking about is not constant, but it increases. The issue is why. Generally, the energy forcings from the greenhouse gases, especially from carbon dioxide, should be proportional to the logarithm of concentration. Not to the concentration, but to the logarithm of the concentration. I have no time to speak about it. But so in last 10 years, the concentrations are rising, but much slower than earlier. But we see the energy imbalance. We can measure measuring energy imbalance in space and measuring planetary heat uptake in situ measurements, especially in the oceans. And we see that now it's about 2 times bigger than it was in the plot I have shown you. And of course, we can see the global temperatures, which surged up rapidly. There is this internal variability, mostly El Niño, La Niña, and this effect. You have a kind of flat temperatures here. If you go to this plot, you will see why. This is this more or less this period of time. And the increase here. And what happened recently, and it's related to our studies, what we are doing at the Institute. First, this is the paper from the end of the last year, which shows that albedo, Earth's albedo, changed very much in last years. 2023 was at this time record year with almost 1.5 degree above the pre-industrial, and the majority was what is called residual, means greenhouse gases. This is the effect of the maximum of the solar cycle. We are now in the maximum of the solar cycle. This is the effect of fact that on the Pacific for a long time there was big area of warm water, which is called El Niño, and this is the jump related to the change of the albedo, which majority occurred in the northern mid-latitudes, partly in the tropics. This is the very recent estimate of planetary albedo, and this is more or less this period 2005-2015, and then you can see decline. Why is it so? This is the map of sulfur aerosol or sulfur emissions to the atmosphere on the oceans from the marine traffic. Total amount of surface around the globe and surface from shipping. And this is from the paper from 2018, but the data are till 2016. And what you can see here, this is the information about international agreements about reducing amount of sulfur in bunker oil. So generally, in 2020, there was huge reduction of the emission of the sulfur, which is not represented here. And you can see the change of the Earth's temperature, energy balance, especially from 2020, except these polar regions are affected somehow by ice. But you can see here in the big part of the northern hemisphere high latitudes, and this is the direct effect of these reductions. How does it work? Well, of course, you can see the last 2 years of day after day sea surface temperatures, and you can see this year. You can see increase and the record values for this. This was the period with El Niño. This is a global average. So the second half of 2023, first half of 2024, and now we have 2025. We are reaching neutral state and La Niña, and still sea surface is much greater than warmer than it used to be. What does it mean, sea surface warmer? It absorbs much less our emissions from the atmosphere. So you can see effect in the increase of the carbon dioxide in the atmosphere due to this effect. So it's not only direct effect of albedo, but due to interactions within the systems, it acts on the output value. And again, the temperatures and whatever. But what was the reason? This is a satellite image which shows over-exaggerated, but shows the real problem. And this is also the problem which influences the cloud properties around the globe. So this is the image from, I think, 2005 of part of the Biscay Bay with some of the stratocumulus clouds. And you can see ship tracks. So changes of the cloud properties, stratocumulus cloud are low over the surface due to the fact that ship passed below the cloud. Why it changed? Previously, clouds had smaller number of cloud condensation nuclei, produce larger droplets by condensation, which reflects the solar radiation weaker. But polluted clouds are whiter. So we have been changing clouds, adding aerosols to the atmosphere, and now we are turning back the effect due to very desirable action not to pollute the atmosphere. To a certain extent, it is being observed also above the ground. And also direct aerosol effects above the ground are also important. So by chance, it is what we are doing at the Institute. Hania Pawłowska had a lot of very good and highly cited papers about the microphysical constitution of the stratocumulus clouds from, and she's working in this microphysics, small droplets. I'm working in cloud dynamics in small scales, but I was also focused on stratocumulus. And our colleagues at the Institute of Geophysics and all the measurement stuff we have here, and we do measurements, is about profiling aerosol, radiative transfer through the atmosphere, and other things. So we see even that also above Poland, we see reduction of aerosol cooling in last decades. This is an example, for instance, how we measure some things. This is from the example of the measurements in stratocumulus clouds over Azores in the mid-Atlantic Ocean, when we had a helicopter and there were two platforms, one measuring radiative fluxes, and the second, which have been dumped down to the cloud along the road, in which we could measure turbulence and microphysics properties in the atmosphere. This is an example that when we moved down to the cloud by fraction of meter, this is the horizontal distance and the slow is not the slip. You know that the structure of cloud, of temperature, of dynamics changes very much. And the stratocumulus clouds are very sensitive to these small scale features on the cloud top. So just summarizing, we are changing the clouds due to change of the whole atmosphere circulation due to greenhouse effect, increased temperatures, and increased big clouds along the equator, which are the source of energy to the big part of the atmospheric circulation. We are affecting not only the large-scale fluctuation, but we are affecting the clouds on the local scale, which are very sensitive to all these dynamical effects and also radiative fluxes, which cool the atmosphere. And we are facing very rapid change, which was hardly foreseen, since we were too much focused on the direct effects of the greenhouse gases. So what in future? We don't know, but there are some elements which can change the stability picture of the climate system in a similar change, in a similar way, like we may change some processes like Rayleigh-Bénard convection and the others. And for instance, what we had, the Earth for a long time was in the situation where noise-induced small changes due to Milankovitch cycles were capable to change the Earth system from glacial to interglacial. And what we are afraid that we will change not this behavior of the Earth system, this is just a kind of stability landscape, but we will change a kind of stability, the whole stability manifold in the climate system. So this is more or less what is being plotted here on this plot. This is time. This was this kind of glacial, interglacial fluctuations. We have added greenhouse gases, so we pushed the Earth behind this part, and we are pushing it toward changing the stability, the whole stability landscape. And this is last slide about this stability landscapes through last 65 million years. We constructed by some dynamic system analysis. And you can see a kind of 1, 2, 3, 2 main and two minor kind of stability landscapes, which have been present. Now here we have been in this very unstable situation. Look for the change of scales, and now we have different perspectives for the future. This is the perspective to 2300. So the question is, which stability manifold will we choose? Thank you.
Questions, please.
First of all, I wanted to thank you, not even for the great talk, but for all the amazing work that you are doing in reaching out to the wide public, popularizing these crucial issues, and I think it's a great example for all of us, so you deserve another standing ovation for this. But for the question, a few weeks ago, Eric Schmidt testified in American Congress that to stay within the AI arms race, United States needs 90 gigawatts of extra energy, and of course it won't be built it won't be got from the nuclear power plants within that time. It will be so-called clean coal, as current president says it. On the other hand, there is a lot of, I wouldn't say hype, but hopes that artificial intelligence will solve all of our problems, and that would be kind of justified. Of course, I'm not asking if you believe in singularity, but in general, how much do you believe that purely scientific or technological advances can save us for this doom, supposing that they are not reinforced through political actions?
This is a good question. I think that they will not solve the problem, since it's not only the energy balance but many other issues. But if you look for this radiative forcing, it means changes in the fluxes from the pre-industrial. Now the kind of forcing from energy use, from fossil fuel mostly, and partly nuclear, but from fossil fuels, is about 0.04 watts per square meter, which is twice less than geothermal energy. But assuming exponential growth of the energy used in the system, we have, of course, some perspective to produce more and more energy, but the energy balance then will look very different, even if we increase nuclear and use, fusion to produce the energy. So there are some limits. As in all physical systems, there are some limits, and I think that first artificial intelligence have some flaws, and we will first have to will have to fight with the floods. But I understand that digging of bitcoins requires huge amount of energy. But generally, the problem is such that if you go to the official statistics of International Energy Agency or International Monetary Funds, you will find that about 7% of global product is being used as fossil fuel subsidized. So these are money which are taken from our pockets just to put in sheikhs and the others. They claim that we will need more and more energy. My feeling that we could use this energy much smarter, and this is a very, very good development for the science, to get as much as you need from the smaller amount of energy processing. And I don't think that investment in, let us say, using more and more fuels, whatever kind of fuel it is, instead of, investing in how could you do better and better using smaller amount of energy, is a right way to proceed.
Obviously, thank you very much for your excellent talk. And I wanted to ask about artificial methods of increasing albedo. Are they discussed among the community, and can you comment on that, like putting some aluminum foil over Sahara or putting back the sulfur aerosols just to increase the albedo?
They are widely discussed. There was a special chapter in the previous IPCC report which has shown many problems with it. The problem is, again, we could do something, and there are plans to do some things better, but we can do it in a good way or in a cheap way. And generally, people try cheap than good. So this kind of thinking that spreading aerosols in the upper stratosphere, which was the idea which somehow tries to mimic volcanic eruptions, is not a good solution because of it influences the atmospheric circulation and especially a water cycle. And we know that after the bigger, we know also from modeling, but we also know from the bigger eruptions, previous volcanic eruptions, that it influences the water supply to big part of Asia. So it switches off the production of food there. So it's not a very good solution. What I like is a kind of idea of John Latham to make these low marine clouds brighter not by spreading sulfur aerosols, but spreading aerosols which are already over the ocean, means sea spray and sea salt aerosol. Then it could make clouds brighter, and it's under control. In any moment, it can be turned off. This kind of spreading high-level aerosols, after you spread, you completely lose control on it. There are also some techniques which are being supposed to remove carbon dioxide from the atmosphere, but these which are efficient are also not very popular, and they are efficient in the timescales of thousands or tens of thousands years. But on the other hand, we see many kind of crazy things like artificial picking up carbon dioxide and storing it elsewhere. So imagine how much energy would you need to do this.
What is the role of excessive agriculture or exploiting rainforest in all this?
I'm not a specialist in excessive agriculture, but if we come to this, I skipped tipping points. Generally, rainforests play important role in both emission kind of aerosols over land and in oops, sorry, I do not have it here. And in water evaporation and in biodiversity. Generally, if you go to the emissions to the atmosphere, now we emit about 40 gigatons of carbon dioxide per year, and about 8 gigatons of it is from deforestation. So from changing carbon storage in natural rich ecosystems into very poor ecosystems we use for farming, and which need additional supply by different products like suppliers. So generally it's a bad role. The second thing is that we observe now, and again this year, that some natural ecosystems became, due to high temperature, emitters of carbon dioxide. And for instance, it has happened in Canadian forests about 10 or 8 years ago, that they changed from the source, from the sink to source of carbon due to increased amount of forest fires due to drought. And drought is another problem in the circulation.
Thank you. For me, it is absolutely clear that what we do, the anthropogenic action increases the temperature, and it is a problem. However, certain accents, I think, could be differently placed. So, for example, you use the term stabilized Earth, as if the past climatic changes were very, very gentle. However, we have very good publications published recently in Nature, in Science, which say that 3,000 years ago, sea level was 23 centimeters higher than today. We had very good publications which say that 1,000 years ago, glacier ice was much smaller in Svalbard. So there were shifts quite abrupt. And we, of course, didn't have satellites to measure it precisely, but very good resolution of ice cores, for example, allows to state that the climatic shifts of at least 2 centigrades within decades occurred in the places like Greenland, or Greenland is the best example. And also, when you see the whole Phanerozoic, at least half of this, 250 million years ago, the correlation between the temperature and the CO2 was 0 or even negative. That places a question mark on the climatic sensitivity of CO2. Thank you.
First, what is obvious from this local analysis, it means that they were local. Not partly not global, and even the authors show the difference. This is you mentioned the Phanerozoic, and this is a kind of recent reconstruction of Earth's temperatures. Oops, sorry. In the Phanerozoic, and you can see on the upper plot the reconstructions of the variability of the global mean surface temperature and carbon dioxide within this period. Just to mention, this is Phanerozoic is very different world. than we have now. Absolutely different. Nevertheless, if you look for the correlation between the temperatures and the carbon dioxide concentration in logarithmic scale, as I said, you can see the pretty clear correlation with reasonable reasonable changes and reasonable agreements. So what I can say? We are based on the physical principles, the energy conservation, laws of thermodynamics, dynamics, and so on, which we believe give us the kind of frames for description of the world. It works pretty well in astronomy. It works pretty well from the micro scale to the big scale. And I don't see the reason why it should not work like this, interpreting the past climates. Since these interpretations, when not based on these basic conservation principles, can lead to some misunderstandings. And my belief is that we have many of such misunderstandings interpreting some local and special paleo data. If we do not try to fit them into the frame of energy balance, mass conservation, carbon conservation, isotopes of carbon, then I would not believe them very much. And there is a kind of story about Lord Kelvin, who wrote a famous paper in the mid of 19th century about secular cooling of the Earth. And this paper made a kind of very big discussion among geologists who said that it is impossible that due to his calculations, Earth should be younger than the majority of the geologists expected. And they criticized Lord Kelvin. But Lord Kelvin exactly wrote, if we will not find an additional source of energy in the Earth's core of the system, my calculations are right. If there are additional sources of energy, they are wrong. And Marie Curie found the source of energy.
Okay, are you able to estimate how many years of accumulation of carbon in the Earth core, surface? Are we burning in 1 year now?
I really do not have the number, I just have the quotation. And the quotation appeared in the paper, which appeared in the year I was born. I was born in 1957. The date is 56 since it's manuscript received, but it was published in 57. And this paper is written by physical oceanographer Roger Revelle from Scripps and nuclear physicist Hans Suess, specialist in isotope mass spectroscopy. And they analyzed different isotopes of carbon just to know what part of emitted carbon dioxide is being dissolved in the ocean. And this quotation is very strong. I think that accumulation of carbon was very different in different epochs. So it's not a single answer to your question.
So let me finish with last one question. Do you think that 1.5 degree warming is already gone?
Yes, I think it is, since the majority of this warming was due to the warming of the upper ocean in last year, and the ocean was much slower than the land, which does not transmit a lot of heat inside. The first thing, and the second thing is that this energy imbalance increased. And it's still part of the energy imbalance if we will reduce more and more aerosol burning fossil fuels. This imbalance will grow more rapidly. And these feedbacks, we know, are positive feedbacks, except for the negative feedbacks of Planck.
So let's thank the speaker again and see you next academic year.